All right, ladies and gentlemen, 3 o'clock. Welcome back to my guest bedroom. Okay, announcements. Number one, homework number 3 for the class on kinetics, which is what we've been talking about this week, will be due on Tuesday of next week. All right, by the beginning of the lecture, just like normal, take a picture, scan it, whatever, send it to me by Tuesday next week. Next thing, your simulation number 1, which is on kinematics, will be due next Friday. No formal report is required for that assignment. I just need you to sort of answer the questions that I ask and submit what I explicitly ask for on that document. Okay, so a little bit of handwritten work, a little bit of MATLAB, sprinkle some salt on there if you want. Send it off. All right, good things. Lastly, tomorrow is a university holiday. However, I still plan on being here at that time to do practice kinetics problems. So we'll do a couple of practice kinetics problems today, and I will continue with a couple of additional practice problems tomorrow. If you can't be there, fine. You can either check out the YouTube video, which I'll post later, or just kind of say, forget it. I don't need to see that. I know kinetics, rar, etc., etc. All right. Looks like I do have a question in the conversation. Nope, it's just telling me that the meeting has started. Okay, good things. Okay, so without further ado, let us kind of pick up where we left off, and we'll start with the slide deck, and I'll sort of voice over some of the things that we talked about last time, and we'll dive in on some example problems, which is kind of going to be the bulk of what we do today. So the last couple of days, we've been going through kind of a lengthy derivation to talk about this analogy between what is F equals ma and the angular analogy that we have for rigid bodies, which is the sum of the moments is Ig alpha. So here we have sort of a long way to sort of get to the equation, which is the sum of the moments is Ig alpha. Your book uses I bar. For whatever reason, they use I bar for the mass moment of inertia. I prefer Ig. So you'll see me write it as Ig, but your book uses I bar. In my notes, I try to be consistent with the book, but I'm going to use Ig. All right, and that was our angular analogy to the sum of the forces equals the mass times acceleration. And then I sort of made a point at the end of lecture last time to say that this general equation, the sum of the moments is Ig alpha, only works if it's at the center of mass. All right, so get all your forces, get all your moments, get all your accelerations to the center of mass, do your analysis there, and then be on with your business. Okay, now there's one tiny exception to that, tiny little exception that I'll talk about in just a second. But when all else is considered, that equation only works if it's at the center of mass. All right. Had a couple slides here to remind you about the mass moment of inertia, and that we can define what the mass moment of inertia is for rigid bodies, for a variety of different rigid bodies that may exist. Okay, thin rods, thin rings, spheres, disks. Here's page number 2 with rectangular prisms, cylinders, so on and so forth. And the mass moment of inertia is different depending on the axis about which you're rotating. Okay, so we see a variety of different formulas here. These are the mass moments of inertia about different axes. So hopefully you pinned this down in ME2002. It should have been something you talked about there. All right. We then moved on to discuss how we actually use this in application. And I first laid out this box example, which is a typical example that you'll see when you first start in on particle kinetics, where you're creating sort of a free body diagram with all of your forces and moments on one side, and a kinetic diagram with all of your accelerations on the other side. And then you equate these things two together. That's kinetics. It's kind of telling you how accelerations performed based on forces, or how much force it takes to drive something with a certain acceleration. So that was for here's your little box example for what would be particles. And then we talked about how that is extended to rigid bodies, so that your forces and moments are, again, on your free body diagram. And on the right-hand side, you have your kinetic diagram, but now you're incorporating this additional term, which is this Ig alpha term, as part of your kinetic diagram. So I did an example with a bike tire, which I think is a little bit more tangible, the bike wheel. But here is just it generally drawn on our mechanics potato, which looks awfully delicious. All right. Last thing I did before we broke yesterday was kind of gave you a strategy of how to attack these kinetics problems. Talked about creating a free body diagram, kinetic diagram, getting everything that you need at the centers of gravity, and then doing your equation, right? So that's kind of where we left off last time. And I want to voice over the PowerPoint slides one more little slide here. And that is some like additional tricks that you might need to execute these kinetics problems. Okay, so some other tricks that you might need to use during these problems is the first trick is if your object is purely in translation. So if your rigid body is purely in translation, there are some things that we know from our discussion about what translation is. So remember when we're talking about translation, translation is all points on the body following parallel paths. So that is kind of this curvilinear motion, or you might just have like this rectilinear motion, which is sort of just like a linear motion. All right. If that is your type of motion, this translational motion, then all points on the body have the same acceleration. So we talked about this with the kinematics, where if you know the acceleration of one point on the body, you know the acceleration of all points on the body. All right. We also know that if an object is purely in translation, that it is not rotating in any way. So if it's not rotating and it's purely in translation, there is no angular acceleration alpha, right? So alpha is equal to 0, and thus your sum of the moments is ig alpha simplifies to sum of the moments is 0, because the right-hand side simplifies down to 0. So for pure translation, you still have these linear acceleration terms, which is like the force equals mass times acceleration. But your sum of the moments as ig alpha simplifies to sum of the moments equals 0, which is something that you've done probably 100 times in your statics class. All right. So that is some tricks that you might have for translation. There's also a trick that you might have for fixed axis rotation. So we'll say if a rigid body is purely in fixed axis rotation about some point O, then the analysis might be easier about the fixed point rather than the center of mass. So usually, like I kind of advocated in the past, get everything to the center of mass, do all your equations and your analysis there. However, the free body or the fixed axis rotation is the only caveat to what I said before. And that when we have the sum of the forces as ig alpha, we typically want to do that analysis about the center of gravity, but the only other place we're allowed to use that particular formula is about a point that has fixed axis rotation. So the takeaway then is that the center of mass and a point of fixed axis rotation are the only 2 points about which we're free to use this general equation, which is the sum of the moments as I alpha. But if you're doing this equation or using this equation about a point with fixed axis rotation, let's say in this particular figure here, this point O, you have to make sure that the mass moment of inertia is selected appropriately, meaning that you're taking the mass moment of inertia of the body about point O, not its center of gravity. So I was like a little bit hesitant to sort of even talk about this because most of what we're going to do in this class is analysis at the center of gravity. And it typically just ends up being easiest when you do that. But there are some situations where if you have fixed axis rotation, things are much simpler if you do analysis about that fixed point. So against my better judgment, I'm going to give you that little piece of information. Okay. Now, without further ado, let's get on with example problems. So we've done a lot of talking, we've seen a lot of math. Now let's see this in action. So here's our first example. We have a uniform 5 kilogram bar. Here, this is bar AB, 400 millimeters in length. It's suspended in a vertical position from an accelerating vehicle and restrained by BC. Okay, so it's sort of suspended in this position from a vehicle, which is supposed to be this sort of gray thing, moving to the left. We're told the acceleration of this vehicle is 0.6 times g, where g is the acceleration of gravity. And we want to determine the tension in this wire BC and the reaction forces at A. So I'll give you a second to sort of copy this down while I prepare my white pad, and then we'll work through the example. All right, so we'll pivot you over here, and we'll get stuck in, as they say in Britain. That was awful. Okay, so here's our example problem. We've got this vehicle moving to the left, and we're interested in the force at A and the tension in BC. So I've kind of copied the givens down here. So we're given that the mass of this particular rod AB is 5 kilograms. The acceleration of this guy is 0.6 g, and I'm going to say it's negative 0.6 g in the I hat. So it's kind of moving to the left. We want to find the force at point A and the tension in BC. Notice here that I've written the force as a vector quantity and the tension in BC as a scalar quantity. That's because tension is a scalar value and forces are vector values. Okie dokie. So we're going to follow the analysis procedure that I sort of laid out a couple of slides ago. All right, I got a question. Can we group up for simulation? No. Continuing. So given the mass AB is 5 kilograms, the acceleration is negative 0.6 g in I. We're going to find the force at A and the tension BC. I don't mind if you work with someone else working through the problems, but don't just like share code freely. All right, that's all I'll say about that. So away we go. We're going to follow the procedure that I laid out in the slides previously. All right, so we're going to make a free body diagram and a kinetic diagram. So first, let's do our free body diagram where we draw all of the forces on our particular piece. So here we're going to do the free body diagram of this rod AB. So here is point A. Here is the center of gravity at G, and down here is point B. Right. Now I want to draw the forces that are acting on this body. If we kind of remember some of the things from our statics class, that if we cut away a pin, we'll have 2 reaction forces. So here we have a pin at point A. So I want to accommodate that pin with 2 reaction forces, one in the X and one in the Y. So here, I'll write this as FA Y direction. And here we have the force at A in the X direction. All right, get your facts straight. At the center of gravity, our weight will act. So right here at the center of gravity, this will be our weight, which we know is mass times the acceleration of gravity g. And the last thing we have to draw here is the tension. We know that for a wire acting on a piece, that the tension will be directed along that particular direction, and we'll have a magnitude. So here, the tension is going to be directed in that general way. And I'll just say that this is the tension in wire BC. It might be useful for us to sort of figure out the angle associated here. You could understand that this is like a 3, 4, 5 triangle, where this length here of BC is 500 millimeters. So if you like your 3, 4, 5 triangles, that's a good way to sort of think about this. Otherwise, if you wanted to figure out maybe, let's say, what this angle theta is here, you could say that the tangent of theta is equal to 400 over 300. That's just by trigonometry. And so you could show here that the angle theta is 53.1 degrees. All right, so we need to define this angle because it helps us resolve the force of that tension into both the X and the Y directions. All right, so that's our free body diagram. All right, now we need to marry that with our kinetic diagram. All right, so again, I'm going to draw sort of a picture of my piece. And I want to do my analysis at the center of gravity. So I want to determine the acceleration components at the center of gravity. So here's my center of gravity at G. All right. I'm told in the problem that this is translating. So I will write translating. All right. So if it's translating, all points on that body have the same acceleration. So with that in mind, all points have same acceleration. And also, if it's just translating, then there will be no angular acceleration. So no angular acceleration, meaning that alpha is equal to 0. Or fish, as they call it, equal to 0. Okay. So I know I have an acceleration. All points on the body have the same acceleration. So if this whole assembly is accelerating with this translational motion, then the acceleration at the center of gravity also matches the acceleration of every other point. So the acceleration at the center of gravity is the same as the acceleration prescribed by the vehicle, which here is sort of in the negative direction, and I'll draw this with red. We're accelerating in this direction with MAX, all right? Where we know that AX is 0.6 times G, where G is the acceleration of gravity. All right, that was given in the problem. Okay, so now I got my free body diagram. I got my kinetic diagram. Time for my kinetics equations. So we're going to equate these two guys. All right, the way that we equate that is by enforcing some of the forces equals MA and some of the moments equals IG alpha. So first things first. Now we do our kinetics. So sum of the forces in X equals, now let's start with Y. There's no acceleration in Y. It makes our life a little bit easier. All right, so sum of the forces in Y is MAY. All right, remember our sum of the forces equation is 2 equations, one in the X, one in the Y. Let's start in the Y just because there's no acceleration in the Y. So we showed, because this thing is just translating sort of to the left, that the acceleration of Y is 0. So that will help us. And let's go back up here to figure out the sum of our forces in Y. All right, well, the forces that we have in Y here are this reaction force at point A. We have the weight of this guy acting downwards, and we have some component of this tension after resolving that tension into the Y direction that will give us our forces in Y. So let's do that quickly. We have the force at A in the Y direction minus the weight of this guy, and then acting in the positive direction as we've drawn it for the tension, plus the sine of 53.1 times the tension BC. This is all equal to the acceleration on the right-hand side, which is 0. All right, so let's put in some numbers. Force at A in the Y direction minus the weight. We're told this is 5 kilograms. So here this is 5 kilograms multiplied by 9.81 meters per second squared. Plus, if you do sine 53.1 on your calculator, you'll get 4/5. Again, remember this is like a 3, 4, 5 triangle. So the contribution in the Y direction is 4/5 of the contribution of the tension. That is 0.8 times TBC equal to 0. All right, well, here we have 2 equations, 2 unknowns. Or sorry, 1 equation and 2 unknowns. So all we can do in this situation is rearrange and solve for one of the unknowns. So let's do that. So let's rearrange, and we'll say that we'll solve for FAY in terms of the tension. So this will be, after some math, 49.1 minus 0.8 TBC, where the units here are newtons. All right, so this is relationship number 1 that we have. So I'll give this guy a little 1 because we know that that's like relationship number 1. All right. So that's the force in the Y direction. All right, we can also look at the sum of the forces in the X direction. So here we have sum of the forces in the X equals MAX. So here we'll take it to the max. Take it to the max. Let's look back up at our picture, get some inspiration. So we have a reaction force here at point A. That's going to be in the X direction. And we have some component, again, of the tension at BC that will also be in X. So my force here is going to be FAX. And then my tension component actually acts to the left. So we subtract that. It's going to be the tension BC multiplied by resolving into the x direction through cosine 53.1 degrees equal to, now we have this MAX term, okay, sort of acting to the left. So we have to put a negative sign in front of it, and it has a magnitude of 0.6 g. So here the mass, sorry, we need a negative sign. So we have negative, the mass, 5 kilograms, gotta give myself a little more space here, times the actual acceleration itself. I'm a little bit out of room, so this is 0.6 times the acceleration of gravity, which is 9.81 meters per second squared. All right, so that's all kind of multiplied together. Sorry about that, just ran out of space a little bit. All right, well, after going through the math, we end up with force A in the x direction minus, if you punch cosine 53.1 into your calculator, you get 6/10. So this will be 0.6 times tension BC equals, on the right-hand side, I have negative 29.4. The units here are newtons. So let's rearrange for FAX. And here we'll have 0.6 T BC minus 29.4 units on this equation, newtons. Here, this is relationship number 2. So here we have FAY in terms of the tension, FAX in terms of the tension. So we have now 2 equations and 3 unknowns. So we need another equation. All right, that last equation that we're going to utilize is the equation that we've sort of been building up this whole week. And that is the sum of the moments is IG alpha. So lastly, we have sum of the moments about point G is IG alpha. Well, since this thing is translating, we know that alpha is 0. Okay, since there's no rotation of this piece. So all we really care about then is the moments that are acting on our piece about the center of gravity. So let's scroll back up to our picture. And here we're focusing in on our center of gravity, which is this particular point here. Okay. So if I'm curious about the moments that act about that center of gravity, well, this force is not going to contribute anything to that because it's passing right through the center of gravity, so there's no moment arm. This guy also passes through the center of gravity, or is on the line of action that passes through the center of gravity, so he doesn't contribute any moment. The only moments that we'll have about the center of gravity will come from this force here that will have a moment arm of this length, and the contribution in the x direction from this force that will have sort of this moment arm length. All right, so that's how we're going to attack this. So thinking about the moment that the force at A will impart about point G, we kind of have to sort of use our shortcuts from statics, our right hand rule. All right, if we're standing at point G, stick our arm in the direction of that force, curl my fingers in the direction of that force, my thumb's going to be pointing into the page. So after looking at the contribution of that force to the moment, we'll have a negative contribution to the moment. So here, from the force at A, we'll have a negative contribution from the force at A in the x direction, multiplied by the moment arm from the center of gravity to that force. Okay, so that is like this length here, which is half of the total length of this piece. All right, so it's going to be 200 millimeters, or if we want to convert to meters on the fly, we'll just say that this is multiplied by 0.2 meters. All right, so that's my moment about the center of gravity that's generated from the force at point A in the x direction. We have a similar idea for what's going on with the tension at point B. We have to resolve that tension into the x direction. So here we'll have a negative contribution from that guy. Stick my arm down, curl my fingers in the direction of that tension. I'll have a negative contribution to the moment. So here this is minus the tension BC times resolving into the x direction, cosine 53.1 degrees, multiplied by the moment arm, which is the same moment arm, 0.2 meters. This all equal to 0. Hopefully this is kind of a nice refresher of your statics class, brush off the moments and all that sort of stuff that you learned a couple of quarters ago. All right, so if we go through this, we're actually going to utilize what is our sort of equation number 2 up here to plug in for FAX, right? So let's do that. And we'll end up with what is negative. I'm going to plug in that relationship number 2, which is 0.6 T BC minus 29.4. That's newtons, multiplied by 0.2 meters. Can't forget your moment arm. Then this is minus, again, cosine 53.1 is 3/5 multiplied by 0.2. We'll end up with 0.12 times T BC here equal to 0. We can solve this guy. The only unknown is the tension. So we'll find that the tension in rope BC is equal to 24.5 newtons. All right, so that's part of the problem, something that we were solving for in this particular problem. So that's nice. All right, so we have this tension. This can go back. So we can plug back into 1 and 2 to find FAX and FAY. All right, so that's just taking that tension value, plugging it back into those equations directly, and you could end up with the following: that the force at A in the x direction is going to be negative 14.7 newtons. Okay, so that just kind of tells us that the original way that we drew that vector was backwards, so that's fine. And the force at A in the y direction here will be 29.5 newtons. So when all is said and done, the force vector at point A is going to be negative 14.7 I hat plus 29.5 J hat newtons. All right, so that kind of concludes this problem. Let's check out if we got any questions in the chat. All right, so that kind of concludes this problem. If you got questions about this problem, now is the time. Notice I was focusing all my analysis about point G. I took the moments there. I wrote the acceleration there. I was looking at point G was my star, right? All right. Doesn't look like there's any questions, so let's move on and do our second example for the day. And I'll put you back on the PowerPoint slides. And here's your second example for the day. It's kind of like a yo-yo going on here. All right. Here we've got a chord wrapped around a homogeneous disk, and this disk has a radius of 0.5 meters. It's also got a mask. Mask is on my mind these days, I guess. It's got a mass of 15 kilograms. If the chord is pulled upward with a force of 180 newtons, determine the acceleration of the center of the disk, the angular acceleration of the disk, and the acceleration of the chord. All right, so I'll give you a second to copy down, and we'll work through. So we'll transfer you over. And let's do it. Let's do it. So here we go. Example number 2. We've got this yo-yo situation going on. We're given that this has a mass of 15 kilograms, and there's a tension from this chord sort of acting upward at this tangent to this circle at point A. We want to find the acceleration of the center of this disk, which is the acceleration at G. We want to find the angular acceleration of this disk, so I've called it alpha disk. And we want to find the acceleration of the rope, which is interesting. Okay, so we'll talk about that once we get there. All right, so let's go. Notice now we don't have purely translational motion. Okay, this guy is definitely going to be spinning. So we can't like assume a translational relationship anymore. We've got to go for our full-blown analysis. So let's go, baby. First, free body diagram. Here's our disk. We have the center of this disk, which is our center of gravity, which is point G. Obviously, this thing's got some weight, and we'll say that that acts at the center of gravity. It acts downwards. We're here. This is W equals mg, the mass of this disk times gravity. And also, we see that we have sort of this like rope that's sort of like wrapped around this guy. And then it's coming off of this disk at this particular location. Maybe a little bit better if I just sort of draw that in black. So it's kind of wrapped around this disk. And at this particular location, it extends upward. And the idea here is that if we looked at what the tension in the rope was right at that particular location, so if we cut this rope and we looked at what the tension was at that particular location, we would see here that this is the tension equal to 180 newtons. All right, sort of the orientation of this force will become important for us when we talk about the moment that that force generates about the center of gravity. All right, so that's kind of why I'm very careful to sort of draw it in this particular fashion. All right, next, kinetic diagram. Draw my picture. All right. Again, I got a center of gravity. It's G. Now my kinetic diagram. Okay. I don't necessarily know anything about the acceleration of this guy in any linear acceleration, any angular acceleration. I don't know nothing. I'm dumb, right? So what I have to do here is just assume that there could be accelerations in all directions and see if I can solve for them. So I'm going to draw that. I'm going to draw for myself here a generic acceleration in the x and say that here we have max. Some generic acceleration in the y, which I'll say is may. I'm drawing them both as positive. Maybe the math later will tell me that they're negative, but for now I'm going to draw them in that direction. And I will also have an angular acceleration of this guy, which I now have to account for. So I'll have an angular acceleration here, and I'll draw it with the positive convention, that is this counterclockwise sort of orientation. Where here this is rotating with kinetic component Ig alpha. So there's my kinetic diagram. I don't know nothing, so I gotta assume that everything there exists. All right, so now we're ready to equate these guys and use our kinematics. So some of the forces is ma, and some of the moments is Ig alpha. So let's get on with it. All right, so here we go. Let's first start with some of the forces x. All right, some of the forces x. Nothing. I don't have any forces in the x. All right, so that means that I'm left with 0 is max. And because the mass is non-zero, obviously, then that implies that my acceleration in the x direction is 0. Well, dang, I hope they're all that easy. So easy a caveman could do it. Right? Right. So that's the kinetic equation that I have x direction. Let's look at the kinetic equation that we have in y direction. Sum of the forces y is MAY. All right, this one's a little bit more complicated. So here, we do have a couple of forces that are acting in the y direction, namely the tension and the weight. So let's get those down. So we have the tension in the positive direction. So we're going to have, I'll just sort of leave it as a variable for now, T minus the weight of this guy, those are my two forces, equals to the mass times the acceleration in y. And I can assign some values to these guys now. All right, so I know that my tension going upwards is 180 newtons, minus the weight of this guy, which is mass times the gravity. So here the mass of this disk is 15 kilograms times gravity, 9.81 meters per second squared, equals the mass of this disk, 15 kilograms, times the acceleration in the y direction. Okay, well, the only unknown in this particular equation is the acceleration in y. So I can solve this for the acceleration in y, and I'll find that the acceleration in y is 2.19 meters per second squared in the direction that I drew. All right, so positive in the direction that I drew. So even though this thing has some weight, it was a little bit unclear whether it was moving down or up. It has the tendency to move down because of its weight, obviously, but it has tendency to move up because I'm pulling up on this sort of object. All right, so in this particular example, the disk is actually moving upwards because of this tension that I'm putting on it. So the total acceleration at the center of gravity is, remember, acceleration is a vector quantity. So we have 0I, so I'll just neglect that. And we have 2.19 j hat meters per second squared. So that is my total acceleration at the center of gravity for this particular object. Sweet. So far, so good. I still have to keep going because I need the angular acceleration. So still need this angular acceleration alpha. So to get that, we're going to use the sum of the moments as IG alpha. So here, the sum of the moments about G is IG alpha, Instagram alpha. Back to my free body diagram to determine the moments. All right, the only contribution to the moments I'm going to have is from this 180 Newton force. All right, the line of action of that force is here. And so the distance between the center of gravity and the line of action of that force is here, which is just the radius of the disk. So the contribution of the moment when I do my location crossed with where the force is going, my thumb will be into the paper. So I have a negative contribution for that 180 Newton force. We'll have that this particular moment is going to be negative contribution from this 180 newtons multiplied by the distance from the center of gravity to the application of that force, which is 0.5 meters, the radius of this disk. So that's the only contribution at the moment I have about the center of gravity. This is going to be equal to the mass moment of inertia of this disk. All right, well, just a reminder, you've got a list of mass moment of inertias on your equation sheet for this class. They're also in this slide deck. So here in the slide deck, common mass moments of inertia, here's our thin circular disk down on the right-hand side. So we're spinning this disk about the z-axis. So hopefully we sort of see this is our z-axis, and we're sort of spinning about that z-axis, which is the center of gravity. So the mass moment of inertia, if we're spinning about that axis, is 1/2 mr squared. So here, this mass moment of inertia is 1/2 mr squared. So this will be 1/2 the mass, 15 kilograms, times the radius of this disk is 0.5 meters to the squared, all times the angular acceleration alpha, which is what I'm solving for. Okay, so now when the dust settles, you can solve for alpha. It's the only unknown that we have. So the magnitude of the angular acceleration is going to be negative 48 radians per second squared. So that means if I want to write this in vector form, that the angular acceleration of this guy, negative 48 radians per second squared, k hat. All right. How are we doing out there? Everybody awake? Looks like I got a question. Someone ask a question? No. Okay, we're good. So we have one last thing that we need to cover in this particular problem, and that is the acceleration of the chord. Okay, which is a little bit complicated, but let's work our way through it. So we still need the acceleration of the chord. So if we think about our picture, we think about kind of the kinetics of what's going on with our picture. Here's our disk. Here's point G. Here's point A where the chord is coming off. So I want to know what the acceleration of the chord is, meaning I want to know what the acceleration of the chord is. Let me give myself a little more space. Sorry about that. I want to know what the acceleration of the chord is. So at any arbitrary location along the chord, after it's separated from my body, I want to know what the acceleration of that guy is. Okay. Well, the acceleration of the chord will be the acceleration at A which is here at A. Here is G, but only the tangential portion. And that's because we have separated at point A as like the tangent to that particular piece. Okay, so what that means mathematically is if we want to write our relative velocity equations or relative acceleration equation, we would typically write that the acceleration of the chord is the acceleration at A, right? Except we're subtracting out the normal acceleration, okay? So this is really like the acceleration at G plus alpha cross the position vector locating A from G plus omega cross R locating A from G. And reminder that this is sort of like my normal and this is my tangent. Okay, so when I say I just want the tangential component, the only equation that I really need here is this equation. I'm sort of neglecting the normal acceleration. And that's because that particular point on that disk is no longer going to be moving back towards the center of that disk. It is coming off of that disk and only moving upwards. Okay, so the acceleration component will only be this tangential acceleration. So from that, the acceleration of the chord is the acceleration of the center of gravity, which is the acceleration of this disk, which here we know to be 2.19 j hat meters per second squared, plus the angular acceleration alpha, which we know to be negative 48 k hat radians per second squared, crossed with the position vector that locates A from G, which is negative 0.5 meters I hat. So finally, the acceleration of my chord is the acceleration of this disk, because I'm pulling the chord upward, plus whatever acceleration is associated with that rope sort of unwinding from the disk, right? So when you actually execute this particular equation, you're going to end up with an acceleration of the chord that looks something like 26.2 j hat meters per second squared. A little bit confusing to think about. We'll sort of see a little bit more of this later, and maybe it'll help to see a few more examples. but we're looking at sort of after this chord has separated, it's only sort of moving in this j hat direction. It's only moving upward. Okay. So again, tomorrow, university holiday, you're not required to come. I'll be doing example kinetics problems. I hope that you come by and take a look. We'll probably be doing a little bit more difficult problems and working our way through those. So maybe seeing a couple more tricks along the way. But other than that, that's it for today. Thank you for coming. Will we be asked a question like that on an exam? Says Shayla. I think I need you to be a little bit more specific. A question like what? So we're generally doing kinetics problems, and you'll have to do a kinetics problem on the test. So yes, you'll be asked a kinetics problem on one of the upcoming tests. Kind of with the rope coming off the edge. Probably not something like that. That one's a little bit complicated. Probably not something like that. But you will have some generic kinetics problem on the test. Are you able to show where you did the moment? Okay, yes, let's do that. So let's go back up. You're talking about the disk problem, right, Austin? Why can I not scroll up? Yeah, there we go. Yes, the disk problem. Okay. So for the moment equation, I'll sort of erase this guy. Let me sort of erase some of these things and I'll sort of start anew. So we had our tension here, T, 180 newtons. And we had our weight here. And our center of gravity is here. Okay, so hopefully we're good on that. So if I want to calculate what the moment is from this tension force about point G, then I want like the moment about G is R, this is A, arriving at A from G crossed F. So hopefully you learned that moments are R cross F in your statics class. Okay. Well, in this particular situation, the moment at G is RAG, which is this length here, this distance here. Hopefully you sort of see that guy. This is the position vector locating A from G. And we're going to cross that with this force here. All right, so this is how we figure out what the moment about point G is. Okay, so the position vector arriving at A from G, this is obviously negative 0.5 I hat meters. All right, it's just the radius of this guy kind of going to the left. And we're going to cross this with the force, which is 180 J hat. With me on that? So if we execute this, the moment about G from that particular force is I cross J, which will give me positive K typically, but I have a negative I component. So this will be what would be negative 90 Newton meters K hat. Clear on that guy?
Yeah.
Okay, good. So when I came down here and I kind of just sort of did that quickly, that was negative 180 times 0.5. That is just kind of going through this calculation relatively quickly. Okay, enjoy your university holiday.